Okay, so this video is for drawing ray diagrams, in particular for imaging point sources like stars and extended sources like moons and planets with a single lens. So just to remind us of some of the stuff that's in a previous video, you need to make sure you're familiar with all the labels for this lens system. So we've got the lens, the focal point, which is where the rays that are parallel to the principal axis on one side of the lens will be focused. The focal plane, which is the plane at right angles to the principal axis, and lined up with the focal point, and the focal length, which is the distance from the centre of the lens to the focal point. Okay, so we're going to be using those words to describe some of the rules we use when drawing ray diagrams, and there are 4 basic rules. 2 of them are very similar, and we can apply them to any situation. We're going to apply them to the 2 situations we've discussed: imaging stars and imaging what we call extended objects, which are not point-like. Okay, they are larger than that, so the moon or a planet. Okay, so here are the rules that you need to be able to use. So we're going to colour code the rays to match the rules that are written in a particular coloured box. So the first rule we have is that any ray that travels through the centre of the lens doesn't change direction. And the basic idea of that is that if you're travelling through the centre of the lens, then the 2 surfaces you're travelling through are pretty much parallel to each other, and so there won't really be any change in direction of that ray. And that's a little bit like what happened to the ray that went into and out of the glass block in our earlier video, just talking about refraction in general. These rules, by the way, only work in the approximation of what we call thin lenses. If the lens gets too fat in the middle, then it's going to be very difficult to use these rules. But all the situations you're going to have to deal with, you can assume, are going to be thin lenses. So that's rule number 1. Ray through the centre of the lens doesn't change direction. Second rule, a ray that's parallel to the principal axis, so that green one up there, on the one side of the lens goes through the focal point on the other side. So you can see that ray is parallel on the left-hand side, and it goes through the focal point, changes direction, so that happens. And again, just a reminder that even though in reality the ray changes direction at both surfaces of the lens, to keep it simple, we just have it changing direction at the centre once when we're drawing the ray diagrams. And the final rule is kind of the reverse of that, that if you have a ray that goes through the focal point on one side, it will end up parallel to the principal axis on the other side. So that's just kind of the reverse of the rule in green we've got up there. So those are our first 3 rules, and the reason they're useful is that you're always going to want to try and draw those rays, because those are the rays that you know where they go. A ray through the centre of the lens, you know where it's going to go. A ray that starts off parallel on one side to the principal axis, you know it's going to go through the focal point. And a ray that goes through the focal point on one side, you know it's going to end up parallel on the other side. So you have to choose those rays to draw when you're trying to work out what's going on with the lens situation. And the final rule is to do with the fact that if you have parallel rays on one side of the lens, then they all converge at the same point in the focal plane on the other side. And in fact, again, you can have a corresponding rule that if the rays come from a point on the focal plane on one side of the lens, they will end up parallel. So you can run that in either direction, okay? But most useful for us is when they start off parallel on one side and end up focused at one point in the focal plane. So those are the 4 rules. We're just going to use those for our different situations. Just before we do that, though, we do have to look at this one assumption that we make when we're looking at stars, and you're supposed to be able to explain this, which is, why is it that the light from a distant star we count as being parallel? So beams of light, rays coming from a distant star, we say those rays are parallel to each other. Well, you can think of it like this. If we have a star here, and then we just draw a selection of rays coming from that star. So I've drawn them going to the right here, and what I've done is I've made each of the rays about 2 degrees apart, and a total spread of 12 degrees across all the rays. Okay, so if you count across, it's 0, 2, 4, 6, 8, 10, 12 degrees across all of the rays there. And we're going to put a telescope at various different locations relative to the star. I'm going to see how big the spread is of the rays coming into the telescope. So this telescope's going to move away, you're going to mark particular positions as we go, and we can look at them. So there's the telescope. Okay, so at the moment in this position it's collecting all of those rays, so the spread of the angles coming into that is 12 degrees because all of those rays are going in. As we move it away, you can see what happens to the spread of the angles coming into the telescope. It decreases. when we go to this point, you see we've got the outer two rays not going into the lens. That means that the spread is only 8 degrees if we count across the rays. And when we go to this point here, it's 4 degrees because there's only 4 degrees across the telescope. So as we can see, what's going on is, as we go further away from the star, the range of angles in the rays from the star that enter the telescope decreases. So we're getting fewer rays entering the telescope, but they are across a smaller range of angles. And we're still relatively close to the star here. If you think about how far away distant stars are, we're talking light years even within our own galaxy, then by the time you get that far away, the angular spread of the rays going into the telescope is going to be tiny, so we can effectively say they're parallel. Okay. In fact, all other stars other than our Sun are so far away that that's true, and even for our Sun, the spread is only about half a degree. Okay, so and that's much closer than any other star is to us. So this approximation that if we're viewing a single distant star, the rays coming from it are parallel is perfectly justified. Okay, so having said that, how do we show what the lens does to that light? Well, it looks very similar to one of our rules. So here's a particular question you might get. Draw a ray diagram to show how a single star is imaged by the lens. The starlight is coming from an angle of 10 degrees above the principal axis of the lens. So I've drawn a little arrow on here, about 10 degree angle. That shows you where the light's coming from. Now again, we have to pick our rays. If you remember, we had the rule that the ray through the centre of the lens doesn't change direction. So that's the one we want to draw first of all, because that's the one where we know where it's going to go. So there you go, there's the orange ray, same colour as before with the rule, and I've marked the 10 degrees on there. Okay? And now it's straightforward, because what we do is we use the other rule, the last one we did, the red one, that says that any rays that are parallel to each other on one side of the lens ends up focused at the same point on the other side of the lens. So then we draw I've drawn 4 more rays. You would probably only need to draw a couple rather than 4 when you were doing it for real. Parallel to the original ray, and we know that if they're parallel on one side, they will meet at the same point in the focal plane on the other side. So you can see what's happened is that basically the light from that star has been focused to a point, and we've produced a point image of the star in the focal plane. Okay, so that's the diagram you draw if you're asked to explain how a single lens forms an image of a star. Parallel rays on one side, focusing to a point in the focal plane, and how you know where that point is you start with the ray through the centre of the lens. Okay. The other thing you need to be able to do is an extended object. So when we draw objects, the traditional way to do it is with an arrow, and we'll see why that is in a second. It's largely so you can actually see which way up the object is. So this could be the moon, for example. Now obviously the moon is going to be a lot further away than just a little bit further than the focal length of our lens, but the principle remains the same here. Okay, if your object is outside the focal length of your lens, then this is the diagram you will draw. There's a different diagram for if the object is inside the focal length, but it's not one that you're required to know, because we only need to talk about imaging objects that are distant. Okay, so once again we start with the rays where we know where the ray is going to go. Our favourite one through the centre. Okay, that one just keeps going. Now that is not enough to tell us where the object is, because to form an image, what we need to do is have a one-to-one correspondence between points on the object and points on the image. So we need a second ray always, and you've actually got a couple of choices. I'm going to show you both of them. We need the other rules that we talked about. Now, there's our first rule. Okay, a ray parallel to the axis on one side goes through the focal point on the other side. There's the focal point. Now you might be saying, but hang on, that ray hasn't gone through the lens. That is totally true, but for the purposes of finding out where the image is, it's absolutely okay to draw a ray that is not going to go through the lens. What you do, you can see I've extended the centre of the lens line, right, outside the lens. Whilst that ray doesn't exist in reality, it still is helpful to tell us where the image actually forms. And similarly, and even more extremely, we can do the other ray, the one that goes through the focal point on this side of the lens and ends up parallel to the axis on the other side. Right, we need to extend the line even further down. There's the one through the focal point on one side, parallel to the axis on the other side, and they all meet at the same point. So that means that we came from the tip of our arrow with those rays, and we are going to the tip of the arrow on the image. So where they cross over, that's where the tip must be. And if the bottom of the arrow is on the principal axis on one side, it will be on the other side as well. Okay, so that defines the position of the image. Once you've done that, if you wanted to, you could draw any other ray that hits the lens and goes to form that image. So we know, for example, that this ray, this top ray, even though there's no rule to deal with that, if the other three rays all meet at the image point, these ones must do as well, otherwise we wouldn't be producing an image. Okay, so that's the diagram for producing an image of an extended object, one where you have to draw an arrow, from a single lens. Okay, last thing then is to point out why we can't really use single lenses very easily for imaging stars and planets. You don't see that done. So what we want to be able to do is control what's called the magnification. Now, in actual fact, what we're dealing with telescopes is angular magnification, which is basically looking at what size of the image is and the object is in terms of the angle that we see in our field of view. I'm going to explain that in much more detail when we look at telescopes, okay? But that's to bear in mind, that's the kind of magnification we're dealing with here. We can't control that magnification in a single lens system. We'd need to be able to do things like change the distance from the lens to the object by a great deal, right? Because what matters is sort of how close the object is compared to the focal length. We can do that a little bit by sort of moving our lens around relative to our eye, but we haven't got full control, okay? So it's not practical to do it that way. Okay, so what we do is we make a system with two lenses, which we call a telescope, which means that we can properly control the magnification, and that therefore makes a much more useful tool for observing things in the night sky. And in a separate video we're going to deal with how telescopes work.